Hello guys, we want to start lecture 25. In this lecture, I want to talk about Fourier series. So we see what definition of Fourier series is, and then we apply Fourier series definition to find Fourier series of different functions. So in the last lecture, we talked about representing a function using one orthogonal set of function or orthogonal set of function with respect to another function. And we saw that we can use one orthogonal set of function to represent any arbitrary function, and we call it Fourier series or orthogonal series expansion. So following set of function is orthogonal on the range of minus p to p. So the set of function contains 1 cosine pi over px, cosine 2 pi over px, and so on until up to cosine n pi over px, and it includes also sine pi over px, sine 2 pi over px, up to sine n pi over px. So we can find this set of function is orthogonal on minus p to p. We can find orthogonal series expansion or Fourier series of any arbitrary function fx on the range of minus p to p using this equation. So in fact, fx is equal to a0 divided by 2 plus the summation of an cosine n pi over px, n from 1 to infinity, plus summation of bn sine n pi over px, n from 1 to infinity. In this case, a0, an, and bn are unknown, so we have to find them. So we have three equations to find them. a0 is 1 over p, the integral minus p to p fx dx. An is 1 over p minus p to p, the integral of minus p to p fx cosine n pi over px dx. And bn is 1 over p, the integral from minus p to p fx sine n pi over px dx. So now we use this definition to find Fourier series of one function. So we want to find Fourier series of fx equal to x plus 1 on the range of minus 2 to 2. In order to find Fourier series of this function, so we have, based on definition of Fourier series, we have fx it's equal to a0 divided by 2 plus summation of an cosine n pi over px plus summation of bn sine n pi over px, and n is from 1 to infinity. Here is from 1 to infinity, and we define it on the range of minus p to p. So in our problem, fx is equal to x plus 1. And so we have p minus 2 to 2. So as a result, p is equal to 2. Now we have to find a0. a0 based on definition is 1 over p, the integral from minus p to p fx dx. So it's equal to 1 over 2, the integral from minus 2 to 2. Fx is x plus 1 and dx. So if you find this integral, you can see that a0 is equal to 2. If you want to find an is equal to 1 over p, integral from minus p to p fx cosine n pi over p x dx. So it's equal to 1 over 2, the integral from minus 2 to 2. fx, it's x plus 1, and cosine n pi over p, so n pi over p is 2 x dx. So here you have to find one integration by part. It's very easy. If you find it, you can end up with this result. So it's 2 sine n times pi divided by n times pi. So you know that sine n pi is equal to 0. As a result, an is equal to 0. Now we have to find bn. So bn is 1 over p. The integral from minus b to p fx sine n pi over px dx. So it's equal to 1 over 2, the integral from minus 2 to 2, x plus 1 sine n pi over 2x dx. So here you have to use integration by part again. If you find it, you can see that it's equal to minus 4 cosine n pi divided by n pi. As a result, we can say that fx is equal to a0 divided by 2. We already found a0 is 2. 2 divided by 2 is 1. An is equal to 0 plus summation of bn. So bn is minus 4 cosine n pi divided by n pi. Bn times sine n pi over px. So it's sine n pi over pp is 2 times x. So we could find Fourier series of this function, n from 1 to infinity. We could find Fourier series of this function. Let's say n is equal to 1. In fact, we want to find the first approximation of Fourier series. So if n is equal to 1, then we can say that fx is almost equal to, we have 1 plus, if n is 1, so we have minus 4 times cosine minus pi. Cosine minus pi is, cosine pi is equal to minus 1. So it's going to be 4 here divided by pi sine pi over 2x. I call it the first Fourier series, or S1x. Now look at this graph. The red line, in fact, is fx equal to x plus 1. The blue one is Fourier series when we have just one term, so it's S1x. So you can see that when we have just one term in the Fourier series, approximation is not accurate. So in fact, Fourier series is not close to the original function. As a result, we have to increase number of terms in the Fourier series. So I find Fourier series when n is equal to 1 and 2. So in this case, fx is equal to, almost equal to 1 plus, if we have n equal to 1, so we have 4 over pi sine pi over 2x. And if n is equal to 2, so we have cosine 2 pi is equal to 1, so we have minus 4 in numerator. Denominator we have over 2 pi sine n is 2. 2 pi divided by 2 is going to be pi, so pi x. I call it S2x is the second Fourier series. So again, the red one is our function, fx is equal to x plus 1, and the blue one is the second Fourier series, S2x. So you can see that it gets closer to the original function. Here we have S3, or third Fourier series. In fact, here n is equal to 1, 2, and 3. So you can see that there is S3x. So the Fourier series is get closer and closer to the original function. Here we have S10x. So you can see that the Fourier series is the blue one, and the red one is x plus 1. So it gets closer and closer. The last one, we have S100. So in fact, n is 1, 2, 3 up to 100. The blue one, it's S100. So you can see that it's very accurate right now. And it covers all the function in the range of -2 to 2. So in fact, we could represent function fx equal to x plus 1 using Fourier series, using some harmonic functions. And as long as we are increasing the terms in the Fourier series, our result is more accurate.